In this short video, we are going to try and understand the traceroute command. So you can call it the traceroute command, the utility, app or program, whatever you want. So this is just like the ping command, and it is usually available across all operating systems. But in case you don't have it, then you can always download and install it because it is a freely available application anyway. And just like the ping command, this is also a application layer utility as per the OSI model. Now, in contrast with the ping command, which uses raw sockets and is purely ICMP based, here there are two possibilities as far as the implementation is concerned. So it's possible that you may use raw sockets, which then use the ICMP protocol, which then obviously means it's operating at the network layer as per the OSI model. But it could also be done through normal sockets, which means it's using TCP or UDP, which operate at the transport layer of the OSI model. Now going back to the ping command, so there the request is in the ICMP protocol and the response also, if it comes back, is based on the ICMP protocol. In contrast, the traceroute utility is a little bit more complicated in terms of its implementation. So here, if the request is sent out either ICMP protocol based or UDP protocol based, then if the response comes back, then it is going to be in the ICMP protocol only. However, if instead TCP protocol is used for sending out the request, then the response again, if it comes back, is also TCP based. Traceroute is used for basic route discovery, network troubleshooting, analysis between the source and target device across a network. Now, before we proceed further with the discussion, I would like to clarify that these two terms, source device and target device, what do they mean? So, source device is any desktop, laptop or phone that you are using, and target device is some other desktop, laptop or server or router across the internet. So what does Traceroute do in the first place, right? Now between a source device and a target device across a network, across the internet for example, there could be any number of routers involved. Now there could be between the source and target device more than one routes, exactly one route or no route at all. Any of these could be possible. Now the Traceroute utility, if there is no route between a source and target, it will tell you about that. And if there are more than one routes between a source and target, then Traceroute will discover or attempt to discover any one route. Now, this technique is actually called outbound path discovery starting from the source device. That is, Traceroute tries to go to the next hop or router or step, whatever term you want to use. I'll use the term hop. So Traceroute discovers the next hop starting from a source device, and then the next hop from there, and the next hop from there, and so on until it gets to the target. Now the traceroute command actually gathers a lot of network related statistics, the most important of which, or at least one of the most important of which, would be the RTT, the round trip time. So this is the amount of time that it takes for a request to get to the target, if it does get there at all, and the response to come back. The same RTT can also be seen in the output of the ping command. Now, the traceroute utility also faces the same danger as the ping command does. That is, administrators may choose to block, just like ping requests, they could block traceroute requests as well. At the firewall level, I mean. Okay, so before we wrap up this discussion and talk about the stuff on this diagram here, uh, if you are already familiar with the concept of time to live, TTL, that would be good. If you are not confident or you don't know about it or you would want to brush up that first, then there's another of our own videos, the link to which I have given in the description below. So you might want to look at that first. Particularly, there's a flow chart in that video which is very important. You might want to go through it and then remember it and come back here. Alright, so let's move forward. So here on the extreme left hand side we have the source device, and on the extreme right we have the target device with a bunch of intermediate routers in between. Now, for this example, I have assumed 3 routers, but in real life there could be more. Now, irrespective of whether the Traceroute utility internally uses TCP, UDP or ICMP, its original authors used a very clever trick when they implemented it. So if an IP datagram arrives at a router in its queue and the router picks it up for processing, if the TTL on that IP datagram is found to be 0, then remember that that IP datagram should not be forwarded anymore. Instead, the router immediately discards the IP datagram and sends back an ICMP time exceeded message back to the source device. All of this has already been discussed in the TTL video which I mentioned previously. So here's the trick. This ICMP time exceeded response message which is sent back from the router which discarded the IP datagram because TTL became 0 contains its own IP address. So when the ICMP time exceeded response message reaches the source device and the source device processes it, it knows exactly which router discarded the IP datagram which was sent out from the source device because the TTL became 0 on that router. So this trick was cleverly used by the original authors of the traceroute command to discover an outbound path starting from the source device, as we are going to see ahead. So you type in the traceroute command at the source device and an IP datagram starts off in an attempt to reach the target device. But its TTL is deliberately set to 1, which means that the moment it reaches the first directly connected router, it will get discarded and that router sends back an ICMP time exceeded response message back to the source device containing that router's own IP address. Now, the second attempt will set TTL to 2, which means this time the IP datagram starts from the source device, gets to the second router, but because TTL becomes 0 at that router, it will get discarded and the ICMP time exceeded response from the second router will contain that second router's own IP address. And obviously for the next attempt, TTL is going to be set to 3, which means it will this time get discarded on the third router and the ICMP time exceeded response from that router will include its own IP address. So going by this logic, as the TTL keeps increasing, at some point, the IP datagram has to reach the target. Now, when it does reach the target device, naturally its TTL would be non-zero, because if it was 0, then how did it get here, right? And since it did reach the target, naturally the TTL should have been non-zero. Now, do keep in mind that as the IP datagram starts from the source device with a certain value for TTL, every intermediate router which processes the IP datagram along the path to the target device decreases the TTL by 1, except for the target device itself, which will just process the IP datagram as it is supposed to be processed normally. So by using this increasing TTL trick and getting the IP datagrams to be discarded by the appropriate routers along the path, Traceroute gets hold of their IP addresses and displays them subsequently in the output. That's how it works.